All right. So this is where we were, right? If you want to know, let's imagine I have a binary tree class, and I don't have a field for size, and I want to know how many things are in there. Well, if you had like a linear structure, you could just iterate over it and count the things, right? Maybe we could do it recursively. But here's how I could do it recursively for a binary tree. And if you're looking at this and you're thinking, like, what's going on? Well, first of all, note that this is really the one we care about in this public one. This is more of a like setup one. I want to call size, and I'm going to ask the root how big it is. Why am I going to ask the root how big it is? Well, I ask the root of a tree how big the whole tree is. And here's how I'm going to do it. I ask, okay, if the node is null, if it doesn't exist, it's 0. There's nothing there. Otherwise, it's 1, the node exists, plus the size of the left subtree and the size of the right subtree, right? So, like, let's think of a case where we have some subtrees. I don't know how big they are. And I say, hey, how big are you? Well, I know it's 1 plus however big this is plus however big that is, right? Now, for all I know, this might be null. So this could be 1 plus 0 plus 77 for all I know. Like, I don't, but that's the idea. 1 plus however big that is, however big that is. Now, this sounds like that classic recursion thing of like, well, we're skipping a step. 1 plus however big that is, well, how big is it? Use a recursive function. Call the same function on that smaller subtree and that smaller subtree. Once they're done calculating how big they are, they get back to me, and I know. So this public one, though, because you'll notice this private one, this is the actual recursive one, it requires a node. Now, if I ask a tree how big it is, like imagine this is within a class. The class has access to the root of its tree, but the root of the tree is probably some private field. So if I ask the class, hey, how big is this tree? I don't have direct access to the root. I would just say, hey, what's the size? With no parameter, and then it automatically calls it on the size of the root. So it's like a starting, it starts the recursive one. That's the idea there. And this is a very common pattern for like recursive things. If you remember back to that recursive linear search, right? Well, technically you could start anywhere. Yes, but often, 1, you would always start at the beginning, but 2, you could make this special function or method that always starts it at the beginning. What's the computational complexity of this? I know it looks, oh, there's 2 recursive calls. Yes, but when I'm talking about the size of the tree, it's going to be called once for every node. Really, it's going to be called like more because like, imagine we have a tree like this where it's null and null. I would call it once here. I would call it for these 2 that don't exist too. So I would actually call it more than n, but it would never be like an order of magnitude more than n. It would be like at most like 2 times n, which is just a constant, so no one cares. Exactly. Who cares? How about contains? Well, here's how you could do contains. Again, we're doing that public thing where we just start with the thing I'm looking for, and then the recursive one takes a current and a needle. And actually, before I explain it, I'm going to give you a minute to look at this code and try to make it make sense. It's always good to try to make it make sense before we really sink our teeth into it. Yeah?
I meant to ask, would it make more sense to have size be the number of elements, or would it make more sense to have it as the number of levels?
The number of levels? Probably the number of elements. You could have another one be like the number of levels, height or something if you really wanted. Yeah, for sure. We could write a function to calculate the height. What would that look like? Oh. Or a method, pardon me. A method to know. What would that look like? That was fun. Suppose the last line's got a little bit of like Boolean logic trick to it, but it's really not too bad. Right? It's pretty cool, right? I'm seeing people kind of go like, oh yeah. Yeah, that's how you can kind of tell, like you kind of see the coolness in this. Yeah.
Would we be expected to write like something like this on the test?
Absolutely. This would be an easy question on the test. Yeah. This like I wouldn't put this on there because it'd be too easy. Yeah. Do we have any questions before I go on to kind of like explain it a little bit? Raise your hand if you look at this and you 100% definitely get it. Raise your hand if you're like, okay, maybe not 100%, but yeah, I'm pretty sure I've got an idea. Okay, cool. Good, good, good. So here's the idea. Look at a node. If it doesn't exist, well, the thing I'm looking for isn't there. By the way, this is going to be very similar to that recursive linear search that we talked about before, where if you ever get to the end and it's not, and you never find it, return false, right? If at any point along the way, so let's think about what it was linearly, right? I've got some linear collection. If I ever get to the end and never find, like, if I'm looking at the thing and I found it, return true, I found it. If it's not the thing, go to the next one and search again. And if I ever get to null, meaning the end of the linear structure, I got to the end and I clearly never found it, return false. False, 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 it's not there. Okay? It's the exact same idea here, but we have that branching idea. So, if we ever see the end, or a node that doesn't exist, it's not there. We didn't find it. If we ever find it, we found it. Otherwise, call it on the next things. Otherwise, like, either we didn't find it, and the whole thing, because we're done, or we do find it, but in between is, well, keep looking. Keep looking where? Well, we have two branches. We keep looking on the left and the right. Now, don't get it twisted. There's an or there, I know, but more on that in a second. So what it means is, let's say I'm looking for some number. And I look here. Okay? And it's not there. Okay, great. So it's not equal. But it's not null, so I don't return false. So what do? I do this exact same thing on this left subtree. Let's say in this example, this left subtree is null. Is it here? False. Okay, return. So this would be false. Or what about the right subtree? No, it's false. Okay, it's not there. Okay, cool. That's the idea. Now, in general, let's say I'm just representing some arbitrary subtrees as these triangles, right? They're filled, who cares? Is it here? No? Look over here. If it's here, this will return true. And then we return true. We're done. It's in this whole tree. If it's not here, you know, we're checking over here. And then go up there, right? Now, what's neat about this one is it's actually short-circuited. Meaning, if we find it in the left subtree, there's no sense searching the right subtree, right? If we find it, we don't need to keep looking for it, right? Meaning, that's why, remember, if you remember, that's the double bars, right? If this is ever true, I don't care about this side. But it could be the case where you definitely do still want to run this method on the right subtree for whatever reason. Not in this case. In that case, you wouldn't want the double bars, you'd want the one. You remember we talked about this? Yeah, cool. All right, so that's the idea. It's basically, does the node not exist? If it doesn't, okay, we didn't find it. If it does, and we found it, we're done. If not, continue searching. But where? Over here? Over here. We have 2 calls. Neat, right? But of course, it could short circuit if we find it on the left subtree. If you don't remember what I mean by short circuiting, true or x equals what? What is the result of this? True or, and I don't know what this is, but what's the result? True. And if this wasn't clear to you, remember, true or true is true. True or false is true. So true or I don't give a shit, true, right? Similarly, if it's false and, same idea, right? False and true is false, false and false is false. So these are where we could short circuit, where I don't actually care about looking over here anymore. If this is true, I can stop. I don't need to go actually check. Like if I go over here and found it, imagine this subtree has 1 billion nodes in it, and I found it, and this subtree has 2 billion. Should I look over here? No, I already found it. So we can kind of stop early, which is nice. But that might not always be the case. There could be cases where maybe you really do want it to run, but often that's a consequence of side effects and some stinky code. But anyways. Order n, cool. Now, what would these traversals look like? Well, here's an example of a pre-ordered traversal. First, you'll see I've got this public one that just starts it. And then we've got the recursive one that here, I'm not doing, it's not returning anything, and I'm just showing you an example. But what would these traversals look like in Java? Well, if it's not null, print it out, do whatever the hell I want with the contents. It doesn't really matter. I'm just printing it out for the sake of just do something with it. Print it out, then do it on the left, and do it on the right. Here's an in order. Here's a way to do it where in order actually, yeah, here's another one. But instead of printing out the contents, add them to some collection. This might be handy if like you want the elements not to be printed out, but you want the elements, you want access to the elements in the order that you want them in, right? If I want all the elements from an in-order traversal and I want them somewhere for some later use, here's a way I could do it. I could just create like an array indexed bag, right? And then every time I do an in-order traversal, instead of printing it out, I just add it to the bag. But this is a very side effecty method, right? If it's unclear what I mean by the side effects, I have one bag, right? Here's my bag. It's an array indexed bag. It's like a list, okay? And every call to in order, I'm going to represent as like, okay, this is a call to in order. It has reference to this bag. So every time we call sequence.add, I'm modifying this bag that exists somewhere else. This bag didn't belong to any like method call. All of the method calls and subsequent like recursive method calls all modify that one bag. This is very side effecty. Okay? You seem to be scrunching your head. Okay, so which part don't you understand? When I say side effect or like let me put it this way. In this right here, how many bags are there? One. This one. And then I give reference to that bag. So instead of printing out the contents, when I do the in-order traversal, I'm going through and I'm adding it to that one bag, right? That bag that is somewhere else in RAM. And all recursive calls all reference that same bag. So like, okay, go on the left subtree and do the in-order traversal, and every time you hit something, you add it to that bag. Where's that bag? It's over there, right? So these methods are modifying the contents of a list that don't really like belong to that method. It's a very big side effect. A pure function would not do something like that. A pure function gets inputs, produces outputs. This is an example that receives inputs, returns nothing, but screws with something else somewhere in RAM. So it's very side effecty. There's not necessarily anything wrong with that, but this is a style of programming that we often try to avoid. But again, we kind of make a lot of exceptions often when it comes to data structures. Yeah?
Could you copy the bag at the thing and return the copy bag with the instruction?
You could, but every time, so here's what would happen. I would have a copy on that side, a copy on that side, and I would somehow need to combine them into a new one. So like, I know what you're saying, but it would end up getting pretty hairy. Yeah, yeah. What's nice though about this is if you wanted to make like an iterator, if you wanted to return an iterator for this, what you could do, now this is really cheesy, but if you wanted to make an in-order, like imagine I wanted to have an in-order iterator, what I could do is just call this method, take the indexed bag, and then return the iterator for the indexed bag. And yeah, it feels kind of dirty, but that's totally exactly what we're gonna do because it's easier. Yeah. So it's kind of like, okay, what I'm doing here is instead of making an iterator for the tree, what I do is I go through the tree, add all the contents to the tree in the order that I want to some other data structure, and then I ask that other data structure, hey, give me an iterator. It's kind of, I'm kind of cheesing it, but it'll work. It'll work. Yeah. Anyways, any questions about any of that?
That's the kind of terrible solution I'd love to see.
Exactly, right?
It's like, don't solve the problem, just create a new one. And solve that.
If I already have a solution to this problem, but I have that problem, just make that problem look like this problem and I'm done.
Exactly.
Right? Yeah. But just don't get caught in the situations where suddenly you think this is the simple part, but it's actually way worse. And the next thing you know, you solve it and you're like, why did I do that? Yeah. Okay. Now, binary search trees are a very special case of binary trees that have a very important rule. Now, we can formulate binary search trees slightly differently depending on our needs, but I'll show you a formulation of a binary search tree. Again, this is not the, this is a definition. So compared to a binary tree, binary search trees have a very specific property and constraints that must be followed. But if we follow these constraints, we get a lot of awesome, cool value, a lot of things we can do with it. Now, you hear binary search tree, and we also learned about something called a binary search. These things are very connected. These properties and constraints can be taken advantage of to improve functionality. So, the definition of a binary search tree. A binary search tree is a binary tree where all values in the left subtree are less than the value in the root node. Okay? All values in the right subtree are greater than or equal to values in the root node. Now, you can find alternative definitions where they put equal values to the left. It doesn't really matter. You just change a couple of things, but the same general ideas still hold. You could also make a version where you don't allow duplicates. Okay, problem solved. Greater than, less than, fine. But anyways, that's a binary search tree. So if you're looking at a tree, and this is the number 77, all values over here must be less than 77. But this also must be true for every subtree within the binary search tree. What I mean is, and I'm sure I've got examples of this, if I have the number like 77, and I have the number 55, numbers here must be less than 55. Numbers here must be greater than 55, but less than 77, because they're to the left of 77. Yeah?
Is the root like the middle point?
Ideally, but we will come to exactly that. Very good question. That would be a nice balanced tree. You could have what we call degenerate trees, which are like, your tree could look something like, you know what, I don't want spoilers. We'll get there. But very good question. So Here are two binary trees. The one on the left is a binary search tree. Why? That property holds for all trees, subtrees here. 8, 12, 5, and 9 are less than 14. 12 is greater than 8. 9 is greater than 8. 5 is greater than 8, 12. Yep. 26, they're all greater than that. These are less than that. This is greater than, yeah, okay, cool. It's fine. But the one on the right, and these can be tricky to spot. The one on the right is not a binary search tree. It almost is. The problem is the 16. You might say, well, you know, it's to the right of that. No, it's not. And it's in its left subtree. Everything down here must be less than 15. And 16 is not. Although 16 is greater than 11, that's good. There's the problem. You see? Yeah. Here is some arbitrary binary search tree. It has no special meaning. It's just a binary search tree. In the above example, note that the leftmost node, yeah, here. Maybe based on what I just told you, what must be true? If I start at the root and go left, 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 left until I can't go left anymore, what must be true about that node? Exactly. It must be. Why? How do I know? Because if it's a binary search tree, and there was a number in this tree less than 3, and it's a binary search tree, it must be to the left of it. And if nothing's to the left of it, that means there must not be anything less than 3. The same holds for this. 15 is the rightmost. Don't think too hard. The rightmost would be like, go right, go right. Oh, there's no more, that's the rightmost. You might be like, is that more right? No, because it's to the left of something. 15 must be the biggest. Why? Because if it's a binary search tree, then anything bigger than 15 must be to the right of it. It must be, or equal to, right? And if there does exist a number in this tree that is in fact actually bigger than 15, then it's not a binary search tree. If it's a binary search tree, it must be the case that it's over here. And if you ever find a counterexample, then your counterexample is not a binary search tree. It's not possible, as the definition stands. Cool? Cool. Now you had a question about, like, is the middle one always the middle? Imagine this tree existed where this right subtree was null, right? The root is 10, and also the rightmost thing. That could happen, right? Now, is that a big deal? Maybe. We'll see. Now, to be clear, a binary search tree is a binary tree. But not all binary trees are binary search trees. But all binary search trees are binary trees. A binary search tree will have all of the properties of a binary tree. Think back to that interface we were defining, that we defined. But we're going to have a few additional operations that we would want to add to our binary search tree. Like things that, by the way, like at this stage of the game, like when we were talking about like stacks and queues and some of the bags, they are very well defined. You add, remove, this is how. These are all the things that you can do with it. With a binary tree, binary search tree, as you get more general data structures, as we generalize more and more and more, there's fewer and fewer must-haves. So you really can add whatever functionality you want to these data structures. There's not as clear rules. So when I say, like, what else might we want? When I say, like, these things, it's not because, like, oh, yes, you need a remove min to be a binary search tree by the definition of by the mathematical definition of a binary search tree. No, a mathematical definition of a binary search tree is relatively vague. As long as it's X, Y, Z, we're happy. What can you do with it? Whatever we want. So that's where when I say, like, oh, we might want to say add, but based on the important ordering, remove, but preserve the ordering, right? Like, remember how with a binary tree we had add, remove, right? Well, how? Well, with a binary search tree, when you add something, like if I say add the number 7, no, add the number 8, no. 6, thank you. By bad luck, I just picked 2 that were already in there. Duplicates could be fine, but whatever. If I say add the number 6, and you go, where do I go? If it's a binary tree, that's a good question. If it's a binary search tree, where does it go? I have an answer for you. Where does it go? Right there. Why? Because it must be to the left of this, but it must be to the right of this, right? To preserve the ordering. If I remove the number 8, well, it must preserve the ordering. If I remove the number 9, like if I remove the number 8, no big deal. If I remove the number 9, if I remove the number 7, some funny things have to happen, right? Yeah.
What does happen if you have two of the same?
Well, our definition says if the number is equal, put it to the right. Okay. So let's say I added a 10. Where would the 10 go? Well, right. Tell me. Let's go. To the right. Where does the 10 go? Duplicates must be, if you have one duplicate, it gets complicated. Yeah. Not really, but there's some nuance to it, right? The leftmost subtree in the right, if a duplicate exists, if there is a duplicate here, it must be the smallest number here, right? Would you agree? If that's not clear, think about it. All the numbers to here must be greater than or equal to, right? If there's a number that's equal, okay, 10. If it's over here, 10 would be the lowest possible value that could exist in here. And based on what we know of binary search trees, the lowest possible thing must be the leftmost of the whole tree. Now, in this case, the whole tree is the right subtree. Now, then again, I could have multiple 10s. So if I added a 10, it would go right here. If I added another 10, it would go right here. And they would keep going like that. And that's fine. Yeah? Where would I put 11? Oh, very good question. Where does 11 go? Well, it's bigger than, it's less than, it's equal, so it goes over here. It would go here. It's the exact same pattern. Very good question. It's the exact same pattern where the leftmost thing in this subtree, if a duplicate exists, it must be there. Because it would go here and then all the way to the left. Now, in this case, it's pretty simple. But here, all the way to the left. And any additional equals would build out to the right. And that's fine. Yeah. But good, fun question. Yeah. I jumped ahead of there a little bit, though. All right, so add. We got to add it a special way. So that's not really like additional functionality, but it's like it would overwrite, I guess, the add in the binary tree interface. Now, it's still an interface. We're not really overwriting. But the add would have a very specific, implementation rules. Same with remove. And then we could have like remove max, remove min, because why not? You had a question?
Yes, if like on the top binary tree you want to remove like the 11, how's it?
It's tricky. There's a lot of rules when it comes to removing. Removing a leaf node, who cares, right? You remove an internal node, well, kind of depends, right? Now, what would work here, right? Well, I need this, the thing here. If I wanted to remove 11, right? I need this number that replaces, and remember, this subtree could be gigantic, right? And let's say this is the case where 11, it doesn't have a left subtree. That's fine. So I need to replace it with a number that is going to be less than everything else in this subtree. Like I want to remove something from the subtree such that the value that goes here now is going to be less than everything in that subtree. Fortunately, that's not too bad. That would be the smallest value over here, right? But, you know, that's a very special case of what happens if it has no left. Oh, like, how are we going to? Yeah, so, you know, it's kind of fun. We're going to talk about the removes, though. Don't worry. This is fun. This is the fun stuff. So, by the way, this is where, like, if that question gets you going like, ooh, interesting, you're good at this stuff. You're going to have a blast in 255, right? 162, We tease the really fun problems. That's the best I can do in 162 because we're still learning, right? But this is now like, it's sufficiently complex, but we can solve it. We can come up with a solution, but it's definitely a little bit more, like there's a lot more like, ooh, we gotta.
If you want to like remove 7, that's
Yeah, what do we do, right? Like, I guess I could put the 8 there. But would that always, like, how would it, oh man, I don't know. We'll talk about it. These are good questions. These are good, fun questions, yeah.
Bad solution that kind of works if you just like take everything that's in its subject
And rebuild a tree? Yeah, that'll work.
rebuild the tree.
Yeah, you could do it, but we could do a little better. But there is potential, yeah, yes it is. It would be. It's definitely a little bit more complex, but it would work.
Yeah.
Okay, so searching a binary search tree. Now, I could do this for searching a binary search tree, right? I want to find a number. Is the node null? No. If it's what I'm looking for, found. Otherwise, look at the left, look at the right. However, because of what I know of a binary search tree, we could be a lot more clever, right? I could say, well, hold on. I'm looking for the number x, and I'm looking at a y. And x, the thing I'm looking for, is less than y. And I have 2 subtrees. Which tree must it be down if it exists? The left one. Because x is smaller than y, and everything smaller than y, if it exists in the tree, must be in the left subtree. It can't be in the right. If it is, it's not a binary search tree. So we can modify this to not say, look at the left, look at the right. We could say, look, no matter what, every time I only need to look at one of the 2 subtrees, which is fantastic. So what do I say here? Imagine looking for 14. No, looking for a number greater than 14. I'm looking for 77. I know it's not in here, right? But I can very quickly know, like, to know if a 77 is in this tree, do I have to go, is that it, is that it, is that it, is that it, is that it? That would be very naive. What I could do is, no, it's not 14, but if 77's there, it must be here. No, it's not 26. If 77, it must be there. Nothing's there, it's not there. Because if it was there, it would be here. And if nothing's here, it's not there. Right? Yeah. So a binary search is very easy to do on a binary search tree. So here's how we do it. It's only a slight modification. If it's not there, it's not there. Otherwise, do the comparison. We're doing this compare to. We ask the elements to compare themselves, whatever. Maybe I should do like an object study, whatever, who cares. I do a comparison. If they're equal, if the result is 0, they're equal. Remember, compare to gives you like a number less than or greater than or equal, if it's 0 if it's equal. Otherwise, if it's equal, we found it. Otherwise, if the comparison is greater than 0, you do it on the left subtree. If it's less than 0, you do it on the right subtree. But no matter what, only one will be called. Only one.